All right. Thank you guys. Thank you all for coming. So I'm Robert. I'm going to talk a little bit about the, so I've been working on an open source project called Ray. And I'm going to talk a little bit about the open source software stack that we see emerging for supporting today's AI workloads. And that involves Kubernetes plus Ray plus PyTorch and VLLM. And I'll talk a little bit more about how they relate to each other, how they get used to with each other, kind of the different responsibilities that each of these, and different problems that each of these solve. But I'm going to start by trying to motivate this a little bit with how AI workloads have changed, because the AI workloads that we see people running today look very different from, say, 5 years ago. I'm going to talk a little bit about what Ray is, because actually, can you raise your hand if you've heard of Ray before? What about if you've used Ray personally? OK, so smaller number. I'm going to share a little bit about just Ray's actor abstraction, because I think that's one of the things that, that I really like about Ray. And then I'll talk a little bit about how it fits into the rest of the tech stack. So this is an open source project we started back at Berkeley. Actually, we were originally not working on systems. So this is Philip and Jan and myself. Philip and I were doing reinforcement learning research and deep learning training research. And it became pretty clear early on that the existing distributed systems that people had at the time weren't really designed for reinforcement learning, weren't really designed for large-scale AI workloads. We tried building some of this stuff on top of Spark. We tried using various HPC systems. But everyone in machine learning at the time was kind of building their own distributed systems in order to run their experiments. And so we got started building tools, not because our goal was to build tools, but actually we just thought we needed it for ourselves. And everyone was excited about reinforcement learning at the time for gaming, and Atari and AlphaGo and things like that. And of course, it was very interesting to see things coming full circle and everyone, reinforcement learning really being used now to build reasoning models and agents and being so impactful. But at the time, it wasn't that big of a community really scaling AI workloads. And the real inflection point in Ray's adoption actually happened in the last year or so. Okay, so we've been working on Ray for a while, but Ray was really designed to solve the challenges that are emerging today. Okay, and I'll talk a little bit about that. So it's really over the last year that a huge number of companies have started using Ray. And one of my favorite examples, we had our Ray Summit, our conference, just last week in San Francisco, and Cursor. Actually, can you raise your hand if you've used Cursor? OK, so a lot of people have used Cursor. So they just built a new frontier coding model called Composer. And it's all post-training with using reinforcement learning to get really good at software engineering. And that was all built with Ray, along with the rest of the software stack for AI. So that's some really impressive use cases in my opinion. OK, so how is AI different today compared with 5 or 10 years ago? Each individual, when I think about different AI workloads, I tend to think about preparing the data, doing data processing. I think about training the model, and I think about deploying the model. And all of those are still happening today. But in each case, there's additional complexity. So in the case of data processing, we're seeing a lot more multimodal data, video data, PDFs, images, and so forth. In the case of training, we're not only doing regular training, we're also doing a lot of we're starting to do reinforcement learning. And in the case of serving, we are not only deploying regular models, we're deploying really large models, and we're composing them together to build multi-agent systems. So each of these different workloads is still around, but is growing in complexity. And I want to go into a little more detail on just a couple of these. So with data processing, the trend that we are seeing is, with the different users that we work with, is that most of the people have always had a large amount of data, right? Companies have been doing big data processing for a long time with systems like Spark or Flink or Hadoop to do analytics, to make decisions, get insights from their data. And most of the data they're working with is data that is nicely formatted in a table or in a database, not because that's the only type of data that is interesting or is useful, but because it's the easiest to work with. Now, if you think about all the other types of data in an organization that a human might consume, whether that is a meeting recording, like a video recording of a meeting, or a PDF, like some contract, or an email thread or a Slack thread, all of that, there's a ton of information and insight and signal in these types of data, but it's really unwieldy to work with. It's just hard what are you going to do with a video, right? You're probably not running a SQL query on it. But we're starting to see a transition or an expansion from tabular data to also all different forms of, all different data modalities. But that's forcing a change in the way we do data processing, because the way you work with a video is not by running a SQL query on it or simple analytics. You're often running inference on this various forms of data, right? And the reason this is possible is that we have more powerful multimodal models, right? Embedding models, vision language models, also new powerful multimodal models that let us actually get insight out of all different types of data, or to structure it, or to make it searchable. And the thing about inference is that inference tends to run on hardware accelerators like GPUs. And so taking all of this together, we are seeing a shift in the nature of data processing, right? In the process of getting value out of data from SQL queries on CPUs, on homogeneous CPU clusters, to inference plus regular processing on a mixture of GPUs and CPUs, right? So this is a pretty big shift. But it's enabling organizations to just get value out of all tons of new different types of data that they weren't working with before. And so I'll talk a little bit about the systems challenges that this introduces. But the second workload I want to talk about is reinforcement learning. Now, this is a figure from a blog post from some researchers at UC Berkeley. We don't really need to understand all of the boxes. The main thing I want to convey is that there are a lot of moving parts if you're doing reinforcement learning. With regular training, the pink box, which says learning algorithm, if you're doing regular training a model, that's the pink box. All the additional stuff is, so in reinforcement learning, part of what you're doing is training a model, and you're using frameworks like PyTorch, or Megatron, or Torch Titan. But you're also using the model to generate new data and then you use the new data to update the model. So how do you generate new data? It's actually a mixture of running inference on the model, perhaps with a framework like VLLM or SGLang, and that model is interacting with some environment. Like if I'm trying to train a coding model, I may have some container running, some Dockerized coding environment where the model is saying, clone this repository and cd into this directory, and then apply this patch, and then run this test. And so it's going back and forth with the model and then the environment, and they're going in this loop to actually try to solve some problem. That generates new data. Then the new data gets sent back to the model to update the model. And then the new model gets sent back to the inference part to generate new data. So there's just a lot of moving parts, right? From a systems perspective, you're managing a bunch of different process groups. There's a lot of data shuffling between them, a lot of coordination. And these are, introduce hard systems challenges. So I want to talk a little bit about so I'm going to transition now to talking about what Ray is by introducing one of Ray's low-level APIs, and to give a sense of how Ray can support these types of reinforcement learning workloads. So this is totally different topic. This is a detour to explain Ray's Actor API. So imagine I want to do reinforcement learning. I just mentioned there's two different parts. I've got training for updating the model, and I've got a generator that's going to generate new data. And I also need to move the weights from the trainer to the generator throughout the algorithm, so I have some get weights and set weights methods. Now this is the Ray part. So Ray lets me add this decorator, and all of a sudden I can take a Python class and add this annotation, maybe specify some certain accelerator types, some memory requirements, other scheduling constraints, And we can use labels, right? You can specify if labels that Kubernetes attaches to the pods. You can specify that in the Ray decorator, so they integrate with each other in this way. And now when I instantiate this class, instead of just spinning up a local object in my Python process, it actually spins up a new process in my cluster with a copy of this object. And so I could spin up one of them, I could start 1,000 of them, I could start 100,000, and they can talk to each other, they can invoke methods on each other. And so all of a sudden you have the building blocks to build pretty complicated distributed applications. So now to actually do the reinforcement learning part, there's a few parts. There's a training part and then generating data. And the way we kick that off with Ray is you can just call the method and then add .remote. So that kicks off the training asynchronously, right? You can wait for the results if you want. You can call generate.remote to kick off data generation, right? And within each of these methods, they might be calling a bunch more methods on a bunch of other actors, right? So there's a lot of stuff hidden under the hood there, or a lot of application logic that can exist. And then in between, I need to move the weights from the trainer to the generator. And I do that by calling get weights on the trainer and then passing that into set weights.remote on the generator. So this basically is how you can, just by passing one object into another method call, sort of transfer data in Ray. And this, these processes might live on different machines. They might use different hardware accelerators. And this will happen, the transfer will happen under the hood. So one recent development with Ray that I want to share is that the way this code is written is not ideal, because the weight transfer, to do this weight transfer the way it's written, the weights have to first move to CPU memory and then are transferred over the network. And in a typical reinforcement learning algorithm, you'll actually want the weights to go directly from GPU to GPU over RDMA. And so Ray recently added native RDMA support, and you can use it by annotating the methods, something like this. Basically, you say Ray dot, you can specify the different transport backend. It's designed to be a pluggable backend, so you can use collective-based backends like Nickel and so forth, or you can use RDMA-based backends like Nixel, and this is something we're planning to add more backends, and this is like a big collaborative open source effort. So just wanted to share, really here with Ray, there's only a few different APIs that we're introducing. It's like the ability to take a Python class and spin it up as an actor. Same thing with Python functions. You can take a function and execute it asynchronously in a cluster as a task. And this is why Ray ends up being very general. So if I think about a lot of other distributed systems, you have systems like Spark, which are designed for data processing, right? You have systems designed for model serving. You have systems designed for model training. Ray is really fairly unique in that it can run all of these different types of workloads. And that comes from having a low-level actor abstraction. Now, since we're talking about reinforcement learning, I wanted to share there's been a renaissance of open source RL frameworks emerging, and from companies like NVIDIA, ByteDance, Alibaba, a ton of different AI companies are open sourcing RL post-training frameworks for LLMs, and the vast majority of them are built using Ray, along with frameworks like VLLM, SGLang, and a number of other frameworks. So, and the reason for that is that there's just, if you look back at this picture, there's a lot of process coordination and management and data transfer and coordination that needs to happen to implement this, and Ray's actor abstraction provides tools for doing that. Okay, so next I want to talk about how Ray fits into the overall tech stack for AI. And I just talked about RL, about multimodal data processing, and there's just a huge amount of complexity with these AI workloads, right? It's much more complex than when we started working on Ray. Oh, whoops. And let's see. So that is, of course, all of this is powered by GPUs under the hood, right? And CPUs and other hardware accelerators. And not only is there growing complexity at the workload level, right, at the top, there's growing complexity at the bottom. You have more GPU failures, more greater scale, more heterogeneity. There are a lot of different types of hardware accelerators and new ones coming out all the time. Okay? Not only do you have chip failures, you have networking failures, right? You have unreliability across in many different places. And because of the growing complexity both at the top and on the bottom, you see there's an emerging need for a software stack that connects the applications to the hardware, right? And that software stack has to solve a bunch of problems. Problems like scale, reliability, heterogeneity, all of these different types of things. And so we've worked with many different companies, hundreds of companies, that have been building out this kind of software stack to scale their AI workloads. And we've seen a common pattern emerging over and over. And so I want to share what the different layers of that look like. So at the top, you've got the training and inference framework, right? This layer is responsible for running the model efficiently on the GPU. And of course, PyTorch is the dominant deep learning framework. And surrounding PyTorch, you've got a rich ecosystem for transformers, right? For different parallelism strategies. So these are some of the common frameworks that we see. But fundamentally, this layer is responsible for squeezing the most performance out of running the model on the GPU. Now, underneath that, you've got the distributed compute engine, which is where Ray sits. And this layer is responsible for solving the distributed systems challenges of scaling. So we talked about process management and coordination, data ingest and data movement, failure handling, resource management, auto-scaling, those types of considerations. And then all of this is typically running on top of Kubernetes, or some kind of container orchestrator, which is responsible for managing containers, provisioning compute, handling multi-tenancy, job multi-tenancy, user multi-tenancy, and much more. And so one of the things that's been exciting to me is that not only have we seen these different layers emerging, but we've actually seen them co-evolve with each other and work better together. And I'll give you 2 examples. So VLLM is an inference engine for running LLMs. And LLM inference has become much more complex because models have gotten larger. And squeezing the most performance out of LLM inference for large models really requires doing a good job at both the inference engine and with the process orchestration. And so the Ray and VLLM open source communities have collaborated to enable fine-grained placement of VLLM workers. And why does this matter? Well, this is important for enabling features like prefill decode disaggregation, right? Where you separate out the prefill stage, which processes the input, from the decode stage, which generates tokens. Each of those different components are often sharded across a bunch of GPUs. You may need co-location of corresponding workers in the 2 stages for performance reasons. This is important for wide expert parallelism support. So think about a large mixture of expert models where you have alternating attention and fully connected layer and expert layers, right? And where the fully connected or the attention layers are maybe replicated across each GPU, and then the expert layers are often sharded across a bunch of different GPUs, and you have to route queries from one GPU to another in a complex way based on which experts are activated. There's a lot of course, there are a lot of different parallelism strategies there. This is important for LLM-aware routing. So you often have a lot of queries going to your LLM that share common prefixes, and so you want to do routing based on where KV cache tensors are cached, right? So there's a lot of details that are LLM specific and are important to get right in order to really get the most performance. And so this, you can sort of see that implementing these features requires solving problems across different layers of the stack. I want to talk a little bit about Kubernetes and Ray. And this is a really nice combination because Kubernetes has has capabilities that it can do to manage containers that Ray is not able to solve at its layer, and around the workload. And Ray sort of handles everything inside of the workload, and so has knowledge and awareness of the workload that Kubernetes doesn't have access to out of the box. For example, both Ray, when it comes to auto-scaling, right, your workload needs to scale up and down. Both Ray and Kubernetes have the ability to auto-scale by adding more nodes or removing nodes from the cluster. But what if to do a really good job, if you want to be able to vertically auto-scale a pod or a container, right, to add more memory to an existing container, Kubernetes has that capability, and Ray has awareness of what's needed inside of the container, what the workload wants, right? There are certain, when it comes to failure handling, Kubernetes is necessary for removing the bad GPUs and things like that from the cluster, or provisioning more compute and getting more compute for a given workload. But then Ray has to work with whatever it's given, right? So Ray can request, maybe you're running a training workload and one GPU fails. Ray can try to request to get a new GPU from Kubernetes, but it doesn't know for sure if that request is going to be fulfilled or not. And if it's not fulfilled, it needs to be able to reconfigure the workload to continue running with the reduced capacity. And so these are the kinds of things that you can do if you have knowledge of both what's happening inside the workload and the ability to control things around the workload and provision compute. This is also important for a lot of companies run training and inference. Now, inference, one simple thing you could do is statically partition your GPUs and use some for training and some for inference. But inference demands go up and down, and so you need to provision for peak capacity, and then that's going to be inefficient. So it's preferable if you can shift GPUs between training and inference, right, as needed. And based on different types of workloads have different priorities. To do that well, you need a great ability to provision compute, to prioritize workloads, and allocate resources between them. You also need the ability to express the workloads in a way that is can handle compute being preempted and can expand elastically to fill whatever compute is available. And so these are the kinds of things you can enable with Ray and Kubernetes working together. Now, the next thing that we recently announced is that Ray joined the PyTorch and Linux Foundation. So we're very excited about this because, well, when we started Ray, we started it as an open source project. We've had a large community of contributors pretty much from the beginning. And a lot of companies have worked together to really design the roadmap. And of course, we were grad students developing Ray in grad school, but we weren't actually running it in production at a company, right? So a lot of the early requirements came from working with various users that were actually relying on it in a mission-critical way. And so the need for the complexity around AI has just grown so much, and the need for this software stack has really emerged over the last year. And so we're, from the Ray community, we're very excited to work with the rest of the open source AI ecosystem to really build out this stack. The last thing one thing I want to share is that I shared Ray's Actor API, right? It's a low-level API for taking a Python class and spinning up an actor. But the benefit of we really think of Ray in two layers. There's the core API that is low level. But imagine now I want to do reinforcement learning or a bunch of data processing or distributed inference on top of Ray. Well, if I'm using that actor API, there's a lot to build, right? I can't just, there's a lot of application logic. And I don't necessarily want to build all of that logic. And so we think of Ray in two layers. There's the core APIs, which are minimal and flexible. And then there's a library ecosystem on top. And some of those libraries, I've been working on. Some of them we've been working on at Anyscale. Some are natively in the Ray repository. But what I'm really excited about is this rich third-party library ecosystem built on top of Ray. Because, and this is something that is similar to Python, right? Part of the reason that Python is so powerful is that not just that it has nice APIs, but rather there's so many amazing libraries built on top of Python, right? Pandas and NumPy and PyTorch and everything. And so similarly with Ray, the thing that excites me is people building powerful libraries on top of Ray, like for reinforcement learning, for data curation, for distributed inference, for agents, and we've seen this from companies like NVIDIA and ByteDance and many others. And so that's something that really excites me about building Ray. Last thing I want to share is that we started Anyscale as a company in 2019 to commercialize Ray and continue developing Ray. And Ray solves a lot of the challenges, like for running the workload in the cluster. What we've been focused on at Anyscale is a lot of the stuff you need to build around Ray to run it in production, right? So providing a native multi-cloud experience, right? Being able to deploy in your own compute or on any Kubernetes cluster, right? Being able to do that kind of workload prioritization where you can shift GPUs between training and inference. Like tons of Ray-aware observability tooling, right? Observability is the kind of thing where you need container-level observability to understand resource usage, resource pressure. You also need sort of workload-aware, process-level observability to understand where's the bottleneck in my application, like where are tasks being queued, where is data being queued, which objects are slow to transfer, all of these kinds of things. And so these are some of the things we've been working on. And I'm very excited to continue collaborating with everyone here on this open source project. So thank you all very much. I'll repeat the question.
So two-part question, right? Some of the things that Ray does are also done in Kubernetes, for example, the schedule. What kind of work is done so that they're not at odds with each other? And the second question is...
well, let me start with the first question. So, well, actually, what was the second question?
Okay. The second question is, what can Kubernetes do more to help like AI workloads work better out of the box?
Okay, so the first question was, Ray and Kubernetes seem to do a lot of the same things, right? And what's the overlap, basically, or do they? And this is actually a question we've gotten a lot. Like, is Ray similar to Kubernetes? Are they different? Because they both seem to do scheduling. They both seem to do fault tolerance and auto-scaling and things like that. This is happening at a different level of granularity, right? Ray is thinking entirely about what happens inside of a workload, right? Like, I already have my containers, which I got from Kubernetes, and now I'm thinking about the process level inside of, coordinating all the processes inside of a container, like scheduling individual functions across different containers, things like that. And so, whereas Kubernetes is thinking at a different level of granularity, thinking about jobs, right? Thinking about containers. Similarly, for fault tolerance, the way Kubernetes thinks about fault tolerance is at the container level, right? It's at the but if you have a bunch of different, if you have a workload, so it's one thing if you have a service running inside of a container and it's replicated a bunch of times and you can just restart the container, right? But what if it's some big data processing job where I'm loading, I have 100, or 100,000 containers that are all running different parts of a single application, right? And where data is being shuffled from one to another, some are running, like inference on GPUs, some are running, are decompressing your videos, and it's not like a thing that can just be replicated. It's actually just all one big workload, and you need every piece. And so, in that case, if a container gets taken away or a new container gets added, something within the application has to understand what do I do with the thing? Do I need to rerun some stuff that was previously executing on that container? Can I load balance stuff across that new container? Like, what can I? There has to be logic handled like inside of the workload. Yeah.
Makes sense.
And then I forgot your second question.
Yeah, the second question was like, how can Kubernetes get better? Like, since you are
there's a lot that's been happening. Some of the things we talked about. How can Kubernetes better support AI workloads? I think a lot of the right things are happening, and I think we've been collaborating closely on these types of use cases, better supporting RL, better supporting offline workloads, right? Great support for all different types of accelerators and sort of topology-aware scheduling and these types of things. So I think a lot of I think the support has been getting really good.
Okay, cool. Thank you.
Oh, thanks for a great talk. I'm just curious about the direction Ray will take together with open source community. More specifically, what does it mean that Ray joined to PyTorch Foundation? And also, is there any, for KubeRay, is there any plan to bring it into CNCF project?
Great question. So what does it mean that Ray joined the PyTorch Foundation? I think most successful open source projects join a foundation, right? There are exceptions, like TensorFlow, React, I think, is maybe not in a foundation. But if you look at really foundational open source or infrastructure projects, whether it's Kubernetes, PyTorch, Linux, all of these different things, it's a natural home for an open source project, especially if you want something to really play, be very broadly adopted across companies, because these things, like at each of these different layers, you tend to have a standard emerge. Like, there used to be many different deep learning frameworks, right? But it has consolidated quite a bit more. People are standardizing on Kubernetes. People are standardizing on PyTorch. I think if you want something to, you tend to have a standard over time. That standard tends to be open source, especially when it comes to infrastructure software. And people are more likely to standardize on something if it's an open source project in a foundation. So it's very natural. And so why join the PyTorch Foundation and Linux Foundation? PyTorch Foundation is just, and the Linux Foundation overall is home to foundational AI infrastructure projects that Ray is used with all the time. And so it's just very natural. We're already collaborating, just as open source communities, and it just made sense to double down on that. And then you asked about KubeRay. So KubeRay is a Kubernetes operator that makes it easy to deploy Ray on Kubernetes clusters, and it's a separate repo in the overall Ray Ray GitHub organization, and we are, as part of the process for moving Ray into the PyTorch Foundation, there are hundreds of repositories in the overall organization, and we are going through one by one and figuring out which ones are make sense to move as part of that donation. And we're still figuring that out with KubeRay. I think they're only Ray is kind of the really substantive part, but KubeRay is super widely used for deploying Ray on Kubernetes. Yeah.
Thank you.
All right. So that will conclude the meeting. Thank you, everyone, for attending the meeting. This wonderful meeting. The rest of the questions will have to held outside. We have another section going.